there! Today we're going to talk about monomials and polynomials and a few of the things that you need to be able to do to manipulate them. So first of all, let's review a little bit. What is a monomial? A monomial is a single term that does not require any addition or subtraction. So for example, the number 3 is a monomial. It's just a single term. 4x is a monomial. It's combined with multiplication, but that's okay. 5y squared is a monomial. Now, when you start including addition or subtraction, you get these polynomials. And a polynomial is a monomial or the sum of monomials. So you could say that 9z, which is a monomial, is also a polynomial. Poly, remember, means many, so most of the time these have many terms. Mono means one, so one term. So another example of a polynomial would be 2b squared plus 19. Or maybe you have 8c to the 4th minus 4c plus 2. Now, a few things that you're going to have to do are going to be to multiply, divide, add, and subtract all of these monomials and polynomials. So today we're going to focus on multiplying and dividing them. When you multiply monomials, you want to make sure you're multiplying the coefficients. Remember, that's the number in front. So for example, 9 is a coefficient. And then you want to add the exponents of the like variables. So let's take this example. We have negative 5x to the 4th times 3x. So what I want to multiply together is negative 5 times 3, the coefficients, and then I have x to the 4th times x to the 1st. Remember, when we don't write the exponent, that's x to the 1st. So adding those exponents, 4 plus 1 is 5. So we're going to have negative 15 x to the 5th. All right, let's take a look at another example. Here we've got several different variables. We've got negative 4x to the 5th y cubed times x cubed y squared. So remember here, when we don't see a coefficient, we're really multiplying by 1. So multiplying the coefficients gives me negative 4 times 1. Then we have x to the 5th times x to the 3rd. So we're going to add the exponents. We have x to the 5 plus 3. Y to the 3rd times y squared is going to be y to the 3 plus 2. So simplifying that gives me negative 4 times x to the 8th times y to the 5th. Now let's just talk quickly about general rules for dividing. When you want to divide two monomials, and this is only true when you're working with monomials, the rules change a little bit when you have polynomials. But when you want to divide two monomials, you want to divide the coefficients, and then you want to subtract the exponents of the variables. So let's take a look at a few examples of division. So here we have 12x to the 3rd y to the 7th z divided by 9x to the 3rd y to the 3rd z squared. I'm going to show you a few different ways of dealing with division, but in this case what I'm going to do is separate out each component. So we're going to look at the coefficient, we're going to look at the x term, the y term, and the z term all separately. So we have 12 over 9 are the coefficients, so I'm going to write that as the fraction 12 over 9. Then my x terms, remember we subtract the exponents, so we'd have x to the 3 minus 3 times y to the 7 minus 3 times z to the 1 minus 2. So simplifying the fraction gives me 4/3. 3 minus 3 is 0, so we have x to the 0. 7 minus 3 is 4, y to the 4th. 1 minus 2 is negative 1, so we have z to the negative 1 power. Now remember, anything to the 0 power is equal to 1. So that little part of the product, that factor, really kind of goes away because 1 times anything is itself. So all we have left in my numerator, think about that stuff as over 1, is 4 times y to the 4th, because those are the only terms with positive exponents. In the denominator, I'm going to have 3 times z, because z has the negative exponent. And remember that rule, when we have negative exponents, they move to the denominator. Let's take a look at another example. And here's another way you can think about how to subtract your exponents, thinking about where your bigger exponents are. So we have 2a to the 4th, b to the 5th, divided by 6a to the 7th, b to the 9th. Now I'm looking at this and I realize, wait a minute, both of the exponents in the denominator are bigger than the exponents in the numerator. That means if I were to subtract them, for example, a to the 4 minus 7, I would get a negative exponent. And then I'm just going to have to move that term back into the denominator anyway. So one way of dealing with this is to just leave the terms in the denominator and subtract the exponents that way. So we're going to take 2/6 times 1 over a to the 7 minus 4 times b, 1 over b to the 9 minus 5. So simplifying that, we get 1/3 times 1 over a to the 3rd times 1 over b to the 4th. Multiplying that all back together, 1 over a cubed b to the 4th. All right, one more example. I think lots of these are good because you can see lots of different ways how your exponents might come into play. 2x to the 6th, y to the 11th, z, divided by x to the 5th, y to the 10th. Now again, I thought about the coefficient of 1 in the denominator, so we had 2 over 1 times x to the 6 minus 5 times y to the 11 minus 10. We only had a z in the numerator, so times z. Simplifying, 6 minus 5 is 1, 11 minus 10 is 1, and then we have z. 2 over 1, of course, is just 2, so I multiply all that together, and we get just 2xyz. All right, this is one that we all love to hate, and that is dealing with our roots of numbers and our radical expressions. So let's first talk about perfect squares. A perfect square monomial has a perfect square coefficient and even exponents. So let's take a look at what this might mean. Let's simplify the following. We have the square root of x to the 6th power. Is 16 a perfect square? It is, because 4 squared is equal to 16. That's how I know it's a perfect square. But what about the variable term? We have x to the 6th. Anytime you have an even exponent, you can write that term as a perfect square by dividing by 2. So x to the 6th is really x to the 3rd squared. Now that's going to help us because it's going to allow us to take the square root. So the square root, or 16, can be written as 4 squared. X to the 6th can be written as x to the 3rd squared. So when I take the square root of each of those, I'm going to end up with 4x to the 3rd. Remember, the square root of anything squared is itself. That's the definition of a square root. What number times itself gives you that? All right, let's look at how we can deal with numbers. Simplifying some other radical expressions. One of the properties you have to know is that if you have a product inside your root, you can separate that product into 2 separate roots. So for example, if you have the square root of a times b, you can think about that as the square root of a times the square root of b. And here's an example of how to do that. Let's say we have the square root of 45. I'm thinking about 45 and I'm trying to think of factors that are perfect squares. Well, I know 9 divides evenly into 45, so I'm going to rewrite 45 as 9 times 5. Then when I do that, I can separate this product out. So instead of the square root of 9 times 5, we're going to have the square root of 9 times the square root of 5. Then I can simplify that square root of 9, and that's going to equal 3. So not square root of 9 times square root of 5 is 3 root 5. Here's another example with some variables and numbers. What if we had the square root of 25 x to the 3rd? Well, again, I'm going to separate that into the square root of 25 times x squared, because that's a perfect square, times x. So simplifying or expanding that into 3 separate roots, root 25 times root x squared times root x. Well, the square root of 25 is 5. The square root of x squared is x. And then this guy has an odd exponent, so we really can't simplify him any further, and he doesn't have any more perfect square factors. So my final answer for this one would be 5x root x. So we're going to do lots of practice simplifying our roots because it is one of the skills that you need to be able to do to identify a correct answer in lots of different places. For example, using the Pythagorean theorem, using distance formula, special right triangles, and working with polynomials and monomials. So we'll practice later today, and we'll see you then.